Okay, so angular momentum. So we know what linear momentum is. We use the letter P. And actually, let me close some of these other files. Okay. So use the letter P. Oh, my stylus has ceased to work. And also, I just realized. Oh, hopefully, you guys are able to hear me. Okay, so I'm going to have to use my mouse. So P equals mv. Angular momentum is this formula. We use capital L for angular momentum. N equals your inertia times omega. That's angular velocity. The unit is kilograms times meters squared over seconds. So it's a little bit different. Remember, the units for this was mass, which is kilograms, times meters per second. But remember, for inertia, that's going to be mass times r squared. So that's why, and then of course you divide by seconds afterwards. So that's why you get those units here. Omega is in rads per second. Not sure why there's a blank there. So omega must be in rads per second. When you rotate something, you exert a torque. So remember, we have talked about that. Rotation does involve torque. More torque equals faster change in angular momentum. And we know this, you know, force times time equals P as well. Remember, we called this impulse. That was from chapter or week 3. We talked about this. So we see something similar for rotation. So angular momentum will equal the torque times time as well. So it's kind of analogous to what we saw for linear momentum as well, or impulse. So there's some formulas we got. Any questions so far? Yep. And then there was a video that was on this too. So the video should discuss this from Khan Academy. Conservation momentum, no different than what we've seen before. So for linear momentum is conserved. As long as our net force is 0, we don't have any external forces coming in. And same thing here. It's also going to be conserved if tau net also equals 0. But we usually don't really worry about that because I present these problems where that is true, so they don't really have to think about that. And remember, initial momentum equals final. And again, initial and final as well for angular momentum. So hopefully that all makes sense. Let's actually now apply this to the problem right below. Then we're going to talk a little about some conceptual stuff on the bottom of this page. And then not sure if I want to do gyroscopes. Don't think I'm really interested in that. So let's do this example down below. Okay, so a 10 kilogram solid disk with R equals 0.4 spinning at 8 rads per second. A 9 kilogram solid disk with R equals 0.3 is dropped onto the first disk. the first disk was initially not rotating, was the angular velocity after disks are to go. So this is a good example of like a collision, if you want to think of it that way. So what we're going to do, remember it's a disk, so there is inertia that goes with that, and that's just like following a solid cylinder, so it's not that much different. So, because remember a disk is this, like this right here, and that's still a solid cylinder. So again, you're going to have disk 1, and we're going to want to calculate each of their inertias. Just get out of the way. So it's going to be 1/2 mr squared so it's 0.8. And then for disk 2, let's get that inertia out of the way as well. And that's going to be 0.45. Now, remember, we want to conserve our momentum, angular momentum. So what's going to happen is that you're going to have initial momentum for the first disk plus initial momentum of the second disk is going to equal the final angular momentum of the first disk plus the final momentum of the second disk. So I'm doing all these subscripts, L01, L02, that's initial, or let's use I, actually, I like I better. So Li1 plus Li2. So initial angular momentum for the first disk plus initial angular momentum for the second disk, that combination is going to equal the final momentum, final angular momentums for the 2 disks. Now, you're told the first disk was initially not rotating. Was angular velocity, hold on a sec. Let me look at this one more time here. Actually, that's a little confusing what they're saying here. So a solid disk is spinning, then another solid disk is dropped onto the first disk. I think what they meant to say, that's kind of a typo. I think they meant to say the second disk. Because clearly the first disk is rotating, so that seems weird to me. So here's what we're going to do. You're going to do, remember, Li is just going to be I omega. So it's going to be I1 times your initial, and then plus I2 times omega 2I. And then, since they're going to be spinning together, you're going to combine their 2 inertias. And we'll call omega final. That's what we're trying to solve for. So you're going to do 0.8 times 8 plus 0.405 times 0, because it's initially not moving, equals a combination, which is 0.8 plus 0.405. Omega F. And we keep going, you get 0.64, or sorry, 6.4 equals 1.205 times omega F. So you solve for omega F, and you should get 5.31 rads per second. so hopefully that makes sense. That's a great angular momentum problem. And I think I would kind of make it clear how to calculate the inertia, so it's not too confusing. I'll just tell you, hey, it's a solid cylinder, here's the formula for it. Then what torque was applied by the first disc onto the second? The collision happens in 0.01 seconds. Now remember, we talked about tau times t equals our angular momentum. And we know that, or the change, actually, that's probably a better way of putting it. So the change in angular momentum for the first disc, obviously was applied by the first disc onto the second. Actually, I think what they meant to say was applied by the second disc. Onto the first. I think that's a typo again. So we do know that tau, or we solve for delta t. No, we want the torque, duh. So tau equal delta L of delta t. So your final momentum, remember the inertia of the second disc is 0.405, and it's now spinning at 5.31 rads per second, whereas initially it wasn't moving at all. And divided by the change in time, which of course is 0.01. And then you could solve for your tau, which will be 215.055 newtons times meter. That's those units for torque.
Where did you get the 5.31?
Oh, from here.
Oh, okay.
Yeah, so the wording I think was kind of messed up in this question. They should have said, because the second disc was not moving. The first disc was, if we're calling the 10 kilogram disc the first disc, right? The second disc was not moving and it kind of just fell down the first disc, and then things changed, right? And so I guess what they're trying to say here is, what was the torque applied by the second disc that fell onto the first disc, or the one that was 9 kilograms when it fell onto the 10 kilogram disc? What is the torque that was applied? So initially, the disc that fell was not rotating. That's why the initial momentum is 0 here. But the momentum it has after it falls and then starts spinning is that. And that, of course, that collision takes place in 0.01 seconds, pretty fast. So you want to know what torque was applied, and that's the torque that was applied, about 215 newtons times meters. Now, again, just to kind of reiterate some things we've already discussed, angular momentum conserved if net external torque is 0. Linear momentum conserved net external force is 0. And kinetic energy is conserved if you have an elastic collision, as we talked about before. I don't know if well, I probably should have this discussion, I guess. We'll talk about direction of angular quantities, but I'm going to skip this part on the gyroscopes because I don't really care for that. Then we'll do some problems after that. So let's keep moving. Okay, direction of angular quantities. So something called the right-hand rule. You'll hear about this often if you take physics in college, especially if you cover electricity and magnetism. So the right-hand rule basically states that if you curl your hand, or if you curl your fingers in the direction of motion, so you can see, like in this case here, if you take your right hand and you curl it this way, your thumb points in the direction of the velocity. So the vector will be in the direction of your thumb. When I say the vector, I mean the angular velocity. So if you turn your hand upside down like this and curl your fingers that way, then the velocity is pointing in that direction. sometimes what some people do, they hold out the hand with the thumb out along the rotational axis. So if you take your thumb and point it in that way, then you expect the disc to rotate. I guess in this case, if you're pointing up, this is counterclockwise. Of course, in this case, that's clockwise. Say a person's holding a spinning bicycle wheel while he stands on a stationary frictionless turntable. What will happen if he suddenly flips the bicycle wheel over, so spinning the opposite direction? So let me kind of give you the fully worked out solution so you can take a look at that, because I think I'll butcher it if I try writing this out, especially because my status is not working. Here we go. So I'm going to clear that. So they say that consider the system of a turntable, person, and wheel. The total momentum before is L upward. So if we assume that, afterward, the total momentum must be the same. So you have to conserve it. So if the wheel is upside down, its angular momentum is negative L. So the angular momentum of the person must be 2L to kind of maintain the same result. So what will happen if he suddenly flips the bicycle wheel over? So basically the angular momentum of the person gets doubled as a result. So again, a person's holding a spinning bicycle wheel while it stands on a frictionless turntable. So think of a turntable like this. It's kind of like a platform, and that can obviously turn. And there's a person standing on it. And he's holding a spinning wheel. Here's a wheel. And you can like hear the, like the spokes of the wheel. And there's like a rod. So he's grabbing the rod and the wheel's spinning. And then if he flips it over, so it's now spinning in the opposite direction. So say it's going like this. And then turns it around, so now it's spinning the other way. That will cause the momentum to change direction, but now the person will rotate as a result. So right now it's stationary, but if you take the bicycle wheel and then if you turn it, your body will start turning as well. I wish I actually had one here because I have a rotating chair, but that's what would happen. So it's spinning, you're kind of like this, and if you turn it, you're going to start moving as well. So that's what we expect to happen. That's just kind of just a physics phenomenon. It's kind of cool. We'll skip gyroscopes. I don't really care for that. And we'll just go and do some problems right now. So we'll probably do all the conceptual problems. So let's look at 6 through 11. I think all those are fair game. Actually, let's do it because 10 might be a little tricky given the answer. So maybe we'll do 10, 11 together. So I want to have you guys do 6, 7, 8, 9 in groups, and I'll give you guys again plenty of time, about 20 minutes. Then we'll come back close to 1. We'll talk about any questions you have. We'll do 10, 11 together. We'll see if we have any time left to go back to 4, 5 if we want to. So again, 6, 7, 8, and 9. The answers are all right there, and I'll have you guys get to work. So let's go back to our breakout rooms, and we'll switch them up. We'll do different rooms this time. So let me